All right. I believe our technology transfer has been completed. So please stop talking to your neighbor about FRBs and cosmology and instead focus your attention to our first speaker, who will be Tarraneh Eftekhari. She will have 20 minutes plus 5 for her presentation, which will appear momentarily. Very good. Please take it away.
Okay, great. So hello, everyone. My name is Tarraneh Eftekhari. I'm a postdoc at Northwestern and a member of the F4 collaboration. I just want to thank the organizers for having me. And I also want to take this opportunity to advertise these very snazzy F4 pins. So if you would like one of your own, please come see me after. So today I want to talk about I want to give a bit of an overview about the host galaxies of FRBs. So both in terms of their galactic scale environments, but also their more local environments. And I'll talk about how these host galaxy studies have helped to inform our understanding of FRB progenitors thus far. And just to set the stage a little, of course, this type of analysis where we use the host galaxy properties to learn about the stellar populations within transients, and hence their progenitors, has quite a long history in the field of transients. So when we look at the landscape of various types of transients, one way we can think about them is in terms of the ages of their stellar progenitors. So starting at the youngest end, we have these very young, very massive stripped O-type stars. These collapse and give rise to jetted explosions like long GRBs and superluminous supernovae. And these tend to live preferentially in ultra-star-forming galaxies and dwarf galaxies. So things that are sort of on or just above the star-forming main sequence. Moving along in age, we have more normal, massive B-type stars that have retained their hydrogen envelopes. And these collapse and give rise to ordinary core collapse type 2 supernovae, and these occur in fairly typical star-forming galaxies. So then we have things like binary neutron stars, binary black holes, and here the progenitor age is governed by what's called the merger delay timescale, or how long it takes for these two objects to come together and merge. And so this is why you wind up with kind of a wide range of progenitor ages. So these objects merge and give rise to transients like short GRBs and the compact object mergers that are detected with LIGO. And they tend to live in kind of the full range of galaxy types, so both star-forming and quiescent. And again, this kind of reflects this wide range of progenitor ages. And then finally, we have degenerate white dwarf systems. These give rise to type 1a supernovae and potentially these so-called calcium-rich transients. And these also live in kind of the full range of galaxy types, so both star-forming and quiescent. And the question we ultimately want to answer with FRBs is, where do their host galaxies lie within this landscape? In other words, what types of stellar populations are driving FRB production? So we can think about this in terms of two main overarching questions. First, what do the galactic scale properties of FRB hosts look like? In other words, what are their host galaxy demographics? And second, what do their more local environments look like? Or more specifically, how are FRBs tracing their sort of local parsec scale environments? And I'll talk a little bit about both of these aspects, but starting first with their galactic scale properties. So the current sample of FRB hosts consists of about 20 or so published events. We heard about many more yesterday, and I'm sure we'll continue to hear about more at the conference this week. But one of the key results that's come out of this initial sample is that there's really a wide diversity of host types, and that dwarf galaxies are not the norm. So the first localization of an FRB to a dwarf was pretty surprising. Dwarf galaxies account for less than a few % of the total stellar mass in the local universe. And so if FRBs are tracing either star formation or stellar mass, then you expect to find them in much more massive galaxies where the bulk of star formation is happening. And so this first localization of an FRB to a dwarf was sort of driving our theories of FRB progenitors for some time and pointing to fairly rare formation channels. And indeed, just last year, we saw another localization of an FRB to a dwarf galaxy. And so this suggests that perhaps some subset of FRBs do form from these more exotic channels. In particular, the localization of FRB2022 to a dwarf was used to invoke this connection between superluminous supernovae and long GRBs. As I said, these live preferentially in these dwarf galaxies. And so this was considered fairly compelling evidence in favor of a young magnetar origin for FRBs. But now, as we've started to amass more and more hosts, we see that FRBs tend to live in much more massive galaxies. And again, so this young magnetar origin is not really in line with that scenario anymore. That being said, it's quite common in the field of transients to invoke magnetar progenitors. So separate from the young magnetars that we think power superluminous supernovae and long GRBs, we have more typical magnetars that form in core collapse supernovae, and then potentially these shorter-lived magnetars that form from binary neutron star mergers. And so this just really highlights that how we connect FRBs to magnetars really depends on the stellar populations within their host galaxies. So as I said, the current sample consists of about 20 or so published events, and it's fairly routine now when we have a new host to try and fit the broadband photometry and spectroscopy and constrain things like the star formation rate, stellar mass, and see how these compare to the general population. So this dark region here corresponds to the star-forming main sequence. And you can see that most FRB hosts lie kind of on or just below the star-forming main sequence, but they do exhibit quite a broad range of both star formation rates and stellar masses. We can look at a color magnitude diagram to get a sense of the ages of the stellar populations. And we see that most FRB hosts kind of cluster around the blue cloud, pointing to young stellar populations where there's ongoing star formation taking place. We do see some hosts in the green valley, which is thought to be where galaxies are transitioning from young to old stellar populations. But ultimately, there is this dearth of galaxies in the so-called red and dead zone, where you have the oldest stellar populations. And what this tells us is that delayed channels or old progenitors are not the dominant formation mechanism. So we can also look at how these properties of the FRB hosts compare to those of other types of transients, as I alluded to earlier. One thing that's commonly explored in the transient literature is the offset distribution. So things like superluminous supernovae and long GRBs have these fairly small spatial offsets, and then short GRBs tend to exhibit much larger offsets due to their large natal kicks. And what we find from this initial sample is that FRB offsets are most consistent with those of type 1a supernovae and ultraluminous X-ray sources. So for those who are not familiar, ULX sources were suggested as a possible FRB progenitor in light of the observed periodicity from a couple of events. So despite this consistency in offsets, the host galaxies of both type 1a supernovae and ULX sources tend to be both more massive and star-forming than those of FRB hosts. So this consistency really doesn't hold up across the board. So indeed, when we add in things like the star formation rate and stellar mass, we find that the majority of FRB host properties are consistent with those of short GRBs and core collapse supernovae. And this is consistent with the picture that we see where FRB hosts kind of span a diverse range of hosts in the same way that short GRB and core collapse supernovae hosts do. In terms of the repeating versus non-repeating population, we find there is no statistically significant difference between the two populations based on this initial sample, and the caveat is obviously that it is very small number statistics at this point. And I'll just go ahead and shout out Shivani's talk later in this session on a new interesting host and how it compares to this population. So one other thing that's really interesting to look at is the emission line ratios for these host galaxies. And this will give you a sense of the dominant source of ionization or excitation within the galaxy. So whether that excitation is driven primarily by star formation or AGN. And what we can see from this figure is that most FRB hosts lie in the star forming and liner regions. But there is this slight excess in line ratios that offsets the majority of hosts from the main star forming locus. And so this sort of begs an interesting question of what type of mechanism is responsible for driving these enhanced photoionization levels. So for example, are these excess line ratios due to a population of AGN where the emission is mixing? And hence, is there sort of an elevated fraction of AGN in FRB host galaxies? Or are these hard radiation fields driven by a population of evolved low-mass stars? And this latter case is what we would expect if, for instance, FRBs come from short GRBs. And so this has motivated a pilot X-ray survey with Chandra that we are currently working on. So this here shows the radioluminosity, X-ray luminosity phase space for AGN, which sort of cleanly divides it into low luminosity AGN and typical AGN. And you can see a few limits for FRB hosts for comparison. So we're focusing on sources where we have existing limits on the radioluminosity, such that we can sort of nicely explore this phase space and get a handle on what the occurrence rate of AGN is in FRB host galaxies. And concurrent to this, we can also look for associated X-ray emission from ultraluminous X-ray sources. So I think we'll hear more about this progenitor scenario in Naveen's talk tomorrow, so I won't say much more about that. But with these Chandra observations, we'll be able to probe ULX sources at the high end of the luminosity distribution. Okay, so that's all I want to say on sort of the galactic scale side of things. Just to recap, we do see this very wide diversity of hosts, and ultimately we need to reconcile this diversity with FRB progenitors. So whether we're sampling the same progenitor at sort of unique evolutionary stages, or whether there truly are multiple formation channels in play. And I'll just go ahead and highlight an e-talk by Alexa Gordon on her work modeling the star formation histories in FRB hosts. So Alexa's also here. I encourage you to check out her talk and chat with her to learn more about this really nice legacy sample of FRB hosts that she's building. Okay, so switching gears and zooming into their more local environments. There have been a number of multi-wavelength efforts along these lines, and I'll just highlight a few of those results. So from high-resolution HST observations, we are finding that at least some FRBs are located in the spiral arms of their host galaxies. However, the FRBs are not in the brightest regions of the spiral arms. And so what that tells us is that although the FRB positions are correlated with regions of star formation, they do not originate from the youngest, most massive stars, and are instead tracing kind of the normal distribution of stars. So within the F4 collaboration, we are also working towards building a sample of ALMA observations for FRB hosts in order to map the molecular gas content. And the idea here is that the distribution and dynamics of molecular gas within these galaxies can allow you to constrain the immediate environments around FRBs and see how they might differ from the rest of their galaxy. So for instance, are there signatures of a gravitational disturbance or a massive stellar cluster? So there have only been a handful of ALMA observations of FRBs to date, and here you can see one such detection. And so with these observations, we can directly constrain things like the total molecular gas mass in these galaxies and see how they compare to the general population. And so that's shown here. So this is the molecular gas mass as a function of stellar mass for a few FRB hosts compared to long GRBs, as well as local galaxies from the IRAM survey. And you can see that these FRB hosts are pretty comparable to the local galaxy group. And so what this tells us is that the star formation mechanism within these FRB hosts is similar to that that's taking place in sort of typical star-forming galaxies. And I will just highlight Marcin's talk later today on an exciting H1 detection. Okay, so zooming in a bit further, we now know that there are two FRBs coincident with persistent radio sources. These are both repeating FRBs in dwarf galaxies. And the prevailing theory here is that the radio emission is powered by some kind of magnetar nebulae. However, when we look at the population of localized events, we see that such radio sources are definitely not ubiquitous. So this plot is showing limits on the radio luminosity for localized events as a function of their redshift. And you can see that we're now probing luminosities well below the 121102 PRS and finding that there are no such radio sources. That being said, it's worth pointing out that most existing limits for PRS emission occur at about 6 gigahertz or below. And in the case of a compact nebulae, so for instance from a magnetar, the emission may be self-absorbed and hence optically thick at lower frequencies. And so this has motivated a high-frequency search with the VLA that we're currently conducting to try and see whether or not we can detect these sources at higher frequencies. And so here you can see a couple of models of different nebulae configurations, and in some cases, indeed, these peak at higher frequencies. So our sample is focusing on FRBs where we have these lower limits as an anchor, and in this way we can really push down on the allowed parameter space with respect to these models. But the fact that we have now two FRBs that are co-located with persistent radio sources and in dwarf galaxies really begs this interesting question of whether or not we can use such sources as signposts for FRBs. So this was the focus of some of our work from a couple of years ago, where we suggested that a number of compact radio sources in dwarf galaxies, or so-called wandering black holes, might actually be analogs of the first repeating FRB. So rather than accreting black holes, we argued that the radio emission may be powered by some kind of magnetar wind. We've since obtained additional VLA observations to constrain the SEDs and the light curve evolution of these events. This work's being led by Vic Dong, who's here and also has an e-talk presenting her latest results. So I definitely encourage everyone to check that out and chat with her to learn more about the project. And she also gives an update on the radio emission from FRB2020 1124A. So just a little teaser. And then finally, I think we'll hear from Casey later today about finding PRS and hence FRB sources in the wild, as well as we'll hear about PRS and this possible connection to dwarf galaxies in a couple of other talks later today. So I won't say any more about that. The last thing I just want to briefly mention is this peculiar discovery of an FRB in a globular cluster. So this is the FRB discovered in the nearby M81 galaxy. And if you zoom way in on milliarc second scales, you can see that it's offset from the center of the globular cluster by about 2 parsecs. But what's peculiar about this, or at least somewhat at odds with our current ideas of FRB progenitors, is the age of the stellar population within the globular cluster, which is of course quite old. And this presents somewhat of a challenge for our ideas about FRB progenitors, specifically those ones that link them to massive stars or magnetar progenitors, because you don't expect such objects to live in globular clusters. That being said, there has been some theoretical work arguing that you can get a magnetar in a globular cluster from a few different delayed channels. So for instance, from the merger or accretion-induced collapse of white dwarfs. But such events are intrinsically quite rare. And so I think this is still a bit of an exciting mystery, but once again, it kind of further emphasizes the challenge ahead of us in reconciling these very diverse host galaxy environments and local environments with this range of progenitor models. Okay, so with that, I'll go ahead and leave up some just sort of top-level conclusions. Hopefully I've conveyed how important and ultimately powerful studies of host galaxies are for our understanding of FRBs and really elucidating their progenitors. I think we are currently in the regime where we are finding new hosts and environments that are really challenging how we think about FRB progenitors. But I expect within the next year, as we start to see the number of host galaxies really ramp up, this picture will become more clear. And I'll go ahead and end there and take any questions. Thanks.
Great. If you have questions in the room, please come to the mic. If you have questions online, I am monitoring the Slack channel. Keith Bannister, please.
Hello, hi, thanks Tarraneh. I thought that was a fantastic talk. You mentioned, I think you had a conclusion that the host galaxy types were typical of Squawk-Galax supernovae, and was it type 1a?
Yes.
And then, but the offset distribution was more similar to long GRBs, I think?
Yes.
So how strong do you think that tension is? Can anything that we know really fit, like standard classes fit inside that, you know?
I'm sorry, can you repeat that last part?
Well, you know, how strong is that tension, or can we really reconcile any of our known source classes or transient classes with either of those things?
Yeah, I mean, I would argue that the sample size is small enough such that there is kind of leeway right now to reconcile these differences. You know, for instance, with the ULX and type 1a supernovae, yeah, so I'm sorry, the type 1a are only consistent in their offsets. And so we don't see this consistency kind of hold up across the board if you just perform these statistical tests. But I do think, given the sample size, it's early to kind of draw these sweeping conclusions.
Cool, thank you.
Okay, there, James here. Thanks very much for the very good talk. I would like to know what sort of molecules did you see in the ALMA observations? You showed, I guess, the continuum. The sort of molecules you detect in the millimeter lines could be very useful for classifying the progenitors. What lines do they see in the ALMA? Do you have any ideas?
Yeah, so these observations are focused on the CO J32 transition. And so that's because the particular sample of sources that we look for, that line is kind of nicely like redshifted in there. As far as other lines, I don't know whether they're seeing any indications, but that's kind of what we're tracing in order to get these molecular mass constraints.
Okay, cool. It would be nice to look for methanol, for example, to check for star formation.
Cool. Okay, yeah, I agree.
Thanks for the nice overview talk. As we'll get more localizations, maybe like one a week or a few a week, do you have any thoughts on how to focus multi-wavelength follow-up efforts?
Yeah, that's a really good question. I think, so we're already kind of finding it challenging, one, to get time for some of the, more distant events in these, X-ray and radio follow-up efforts. So I think focusing on the most nearby events will definitely be like most fruitful, just in terms of sensitivity and, when the level at which you can get limits that will be constraining for models. So that's my thought as far as kind of multi-wavelength observations.
Thank you.
Yeah, thanks for a great talk. I just wanted to comment on the persistent source in 1905-20b. I'm actually not quite convinced yet that it is a persistent source, because we haven't seen a VLBI image of it yet. It's a VLA of, beam size 360 milliarc seconds, I think. So I'm still curious to see a VLBI image at, say, 5 gigahertz to see if it really is a persistent counterpart, because in R67, so 2011-24A, there was apparently a persistent counterpart, which on VLBI scales, there was none. So just caution that, there might not be a persistent source at all.
That's fair, yeah.
Here's an online question from Jason Hessels. Dr. Eftekhari, why aren't we seeing more FRBs hosted by galaxies on the star-forming main sequence?
Yeah, that is an excellent question. And I don't know the answer to that. I think I will, again, highlight Alexa Gordon's talk on constraining the star formation histories. She's doing some very nice non-parametric modeling, which I think is not traditionally done in host galaxy studies. And this does tend to lead to some systematic offsets when we look at, for instance, the star forming main sequence. And that discrepancy may or may not go away when you include this non-parametric effort. So more reason to check out Alexa's talk and chat with her.
And one from Clancy James. If there are two progenitor classes, what are the prospects for separating them?
Yeah, I mean, I would hope that as we build a larger and larger sample, we'll kind of start to see these two classes of events like clearly bifurcate on a number of these figures that I showed. You know, there's also other differences that we might be seeing between different classes, for instance, this XSDM that we talked about. So I'm fairly confident that the hopes are high, prospects are good. Once we have a pretty large sample, I think that these things will kind of start to reveal themselves.
Great. Well, let's thank Tarraneh again. Our next speaker is in the room, not as scheduled online. Adaeze Ibik, please come down. Or am I mistaken? Nope. Very good. She's there. This will be a 10+3 talk. And please proceed.
Hello, everyone. My name is Adaeze Ibik. I'm a PhD student at the University of Toronto, Canada. I'm working with Professor Brian Gensler, Professor Maria Drought, and amazing people from CHIME, FRB, and real fast VLA collaborations. I'm happy to talk about this project, the search for persistent radio sources associated with repeating fast radio bursts with CHIME, FRB. One of the reasons why we want to undertake this study is, just like the last speaker said, we want to add to our knowledge towards understanding fast radio bursts. And as we all can agree that identifying their host galaxies as well as understanding their local environment would together help to constrain the progenitor channels as well as their emission mechanism. And also we would like to see if probably there are some preferences to repeaters or maybe different from one-offs, and we'll see that in the presentation. Okay, so to date, we now have associated two repeating fast radio bursts to a persistent radio source, which I will be calling PRSs going forward in the talk. And the last presenter has nicely described these persistent radio sources very well. I'll just mention that the two PRSs seem to have some similar characteristics, like their flux is of 0.2 millijansky, and they have luminosity of 10 to the power 29 per second per hertz. Even though they have different spectral shape, they are quite offset from their host galaxy center. So I see also different people coming up with the possibilities of trying to explain this radio emission. These have formed our FRB PRS models so far. Some of them I've listed, and I'll be talking about them also in the later slide. Right, so even though we have these two detections of PRSs from repeaters, we have also recorded deep upper limits in the community for some FRBs, like I've mentioned, I've listed here, where we do not see a persistent radio source. And so it's not clear if there are some preferences with finding PRSs with repeaters or not, and it's still also not clear what distinguishes FRBs with this, So it's important that we find many of these things in order to clearly, differentiate things. So for this work, we are looking for FRB 121102 kind of unresolved radio sources within the CHIME FRB repeater regions. And to this, we'd like to eliminate active galactic nuclei by requiring that the PRSs is offset from the center of this host galaxy. And for the cases where they are close, we require that the radio to optical flux ratio is less than 1.4, which is like the threshold where we expect star formation activity. So to interpret these sources, we consider their luminosities and their spectral shape for this work. I would like to mention that the luminosity here were calculated using the spectroscopic redshift for the ones where we know them. And we also use the maximum redshift from the DM for most of them. And we search both archival data and dedicated deep VLA images for this. Just to give us a bit of context, that the CHIME FRB localization regions are in the order of 1 arc minute, and so all of the PRSs that I'll be talking about here are candidates for association with the FRBs. So for the archival search, we cross-matched more than 40 FRB repeaters with public catalogs, in particular VLAS being the most sensitive one, where we have 1 sigma RMS value of noise of 0.12 microjansky per beam. Here we found very few radio sources in the field with a probability of chance coincidence more than 99%. However, here is an example of where we find a VLAS source. Here the red region is the CHIME FRB region, and the green area gives you the position of the PRS. We could get a Lycov and SCD for these, and this shows a flat spectral shape, even though we are in the process of getting optical spectra with the Gemini note in order to characterize the emission better. So the takeaway from the archival search is that PRSs are not common at the luminosities probed by current public catalogs and images. And we demonstrate this result showing this radio luminosity versus redshift plot, where you see all of the upper limits from the VLAS in context with the 2 PRSs that I've mentioned that we have now associated. And so in particular, the horizontal line is the PRS luminosity for FRB2022. And we could see clearly that, that the VLAS can only detect PRS's luminosities at low redshifts. Okay, so in order to see even fainter radio sources, we have to collaborate with RayFast VLA. We have been observing some FRB fields, like taking deep images in the L band with VLA. And 8 of these FRBs, we worked with obtaining RMS value of their image down to 3.5 microjansky per beam, which is 30 times deeper than what we could get with VLAS. Now, this allows us to probe potential PRSs even at fainter luminosities. So, out of them, 3 of them, we do not have any PRS within their field, and I'll be showing some of the examples in the later slide. But then for some of them, we do find some compact radio sources in the field. So here is a typical example where you could see a radio emission from, this is from the 2 merging galaxies you see in the optical. This is clearly a radio emission, but definitely not a PRS. And so we place deep upper limits on the presence of a PRS for this case. Here is an exciting discovery we found of a massive spiral galaxy that is close by to us, that is a protective host of this FRB. Here we could find an unresolved radio source at the edge, which we searched public catalogs, and in the absence of infrared and optical counterparts, we argue that this could be a PRS for this FRB. Here is again another example where the PRS candidate in this case is coincident with a faint galaxy. And so we're in the process of obtaining optical spectra in order to characterize this emission better as well. Right. So just to show the luminosities of some of the PRS candidates found from this work, I'm showing this plot where of interest is the fainter luminosity object that we are able to find, fainter than FRB2022 PRS. In particular, we see the previous spiral galaxy that I showed. The PRS is the one that you see here in 10 to the power 26. So if I go back, this particular one. And so even though it's a low luminosity PRS, we think that this is a real, a case to look into more details. There are also some brighter ones, like the one with the faint galaxy showing up here, the one also on the last slide here. Okay, so what are the implications if the PRS candidates are associated with the FRB? So for this, we are considering some models that have been used to describe the FRB2022 PRS. Some of them have been described very well by the last speaker, Tarraneh, so I won't go into so much detail. But I want to discuss the last one, the expanding supernova rejector case. So this, in particular, we used an analytical solution to model the synchrotron self-absorption combined with synchrotron emission and free absorption to produce spectral energy distributions and, of course, their energetics, in particular the pre-explosion mass loss rates, the shock velocity, and the radius of the emitting material. So the results showing here are just a few of the results where the allowed SEDs are plotted as well as the allowed parameter space for the energetics. So of interest, for the first plot, which is the SED from that particular PRS associated with the spiral galaxy, this velocity that we see here is consistent with what you expect from a superluminous supernova, whether it was the type 1 or the type 2. Whereas the second one, which is the PRS from the faint galaxy, I showed here as well. So that case, the shock velocity, as you can see, is quite large. Now, this rules out any kind of normal supernova and superluminous supernova. Instead, this is looking relativistic. And so we argue that this could be consistent with relativistic supernova or even gamma ray bursts. So we see that some of our PRS candidates could fit luminous supernova rejector running into a CSM. CSM is the circumstellar material, And for some of our objects, it implies high ejector velocity, similar to relativistic supernova. Okay, in summary, we'd like to say that PRSs are not common at the luminosities probed by current public catalogs and images. And the deep imaging shows some promising candidates and would need better localization to reveal the associations with the FRBs. We found more than 6 PRS candidates at flux level deeper than the VLABs, and we used Gemini spectra to obtain their redshift as well as check for variabilities. The PRS could be consistent with luminous supernova, ejector, relativistic SN, and some of the FRB theory that I highlighted earlier that we'll be looking at, and it will be interesting to see what these emissions are. I will stop here, and I'm happy to chat on the FRB Slack, or you can email me as well for this. Thanks.
Please.
These are exciting results. Do you have RM measurements for these 6 candidates? And if the RM measurements are large compared to the rest of the FRBs, are they similar to 190520 or 121102?
The rotation measurements?
Yeah.
Yeah, so the rotation measurements are not crazy, but we have one example that have the highest RMS so far, and it also has a high DM, and I think we'll be having some follow-up with that, with the EVN. I'm not showing that here, but definitely we do have some exciting, coming results. But the other ones are not crazy, if that is what you're asking.
Do you have any, of these 6 sources, is there any one source with a very low RM, like 0 to 100? Yeah.
Potentially it's possible, but I don't have the number off the top of my head.
All right, thank you.
Yeah, thank you.
Liam?
Great talk, that's really cool work. Can you say a little bit more about the FRB 2018-1030? Is it a repeater? What's its dispersion measure? And do you know how far away that galaxy is?
This one?
Yes.
Yeah, so these FRB have been published, and the host of the Galaxies and NGC, of the FRBs and NGC Galaxy, is actually a nearby one. So is a repeating FRB, is not active right now, and I don't have the number of the RM on top of my head, but I can check and I can report to you on Slack. So, well, I don't know what else you want me to talk about on this, but the PRS itself is a bright one, but I think it's because it's close by. And so we find that the luminosity shows that it's actually a faint source, right? We did search through even the C catalog, which is a deeper optical image. We searched through the infrared catalogs and images, and there was no coincident source at that position, which is, weird. And so we thought that this could be a potential PRS for that FRB. Even though we do not have like a localized position with it, maybe VLBI or something, but I think it's an interesting FRB, for people to look out. Yeah.
Thank you.
Thanks.
Thank you. We've run well past the 13 minutes. Sorry, Casey. Ask your question. It's like, thank you, Ms. Ibik, for your presentation. Next up, we'll have Calvin Leung, who I think is online.
Hi, can everyone hear me?
We hear you.
Okay, great. Sorry, I didn't get a chance to do a tech check before this. Before I start my talk, I want to start with this slide that Evan showed yesterday. I think it sets the stage for my talk really, really well. In this slide, Evan points out the status of CHIME as sort of the Achilles in the FRB survey world, but also points out our Achilles heel, which is that one-off CHIME FRBs are generally not localizable to their host galaxies. The title of my talk today is a one-off FRB localized to its host galaxy using VLBI with CHIME FRB. My name is Calvin Leung. I just finished my 4th year as a PhD student working with Kiyoshi Masui, who you've seen in discussion sessions. I am going to be on the job market this coming cycle. So if you have positions in radio interferometry, FRBs, cosmology, I would love and have a chat with you. Before I go on, I want to emphasize that the results I'll be presenting today are the culmination of years of work, really hard, really technical radio interferometry, as well as dedicated observations by members of the CHIME team, and I'll try to highlight some of the most significant contributors to this work as I go along. So how do we catch a FRB and VLBI at the time of detection? I think this GIF sums it up better than I could possibly try to describe to you in words. The idea is that CHIME scans the sky, a wide swath of sky for FRBs, and every time we detect an FRB, we tell our friends. In this case, our friends are 2 telescopes, one in Algonquin at ARO, and one in Green Bank at which is called TONE. And ARO and TONE are these two little telescopes which shadow the CHIME beam at a declination of 21. And any time that we detect an FRB with CHIME, we send triggers to ARO and TONE, tell them to dump data, and then we do VLBI with a custom VLBI correlator that we built just for this purpose offline. Our 3-element VLBI array consists of, has 2 3,000-kilometer long baselines, which gives us a resolution corresponding to about 6.6 megalambdas. We don't use a 3rd baseline because those 2 dishes are very small and insensitive compared to CHIME. And we get our north-south information just by combining these 2 mostly east-west baselines, but sort of tilted a little bit so that you have some north-south information. Before people get confused, this is not the CHIME outriggers effort. These are outrigger pathfinders. My colleague Jane has a recorded talk on the wide field cylinders that we're building to do this kind of science, localization with VLBI at the time of detection on a large sample of FRBs, not just the ones at a declination of 21 degrees. I don't need to tell you more about CHIME. It's the Canadian Hydrogen Intensity Mapping Experiment. It's a phased array beamforming interferometer working at sub-gigahertz frequencies with a 1 arc minute synthesized beam. But I will tell you about some of our friends. There's a 10-meter dish at Algonquin Radio Observatory. My good friend and colleague Tomas, who's now a prof at University of Chile, refurbished this dish and used it to do the first triggered single pulse VLBI on 3,000-kilometer baselines. And we measured the crab pulsar a bunch of times and characterized clock drifts, and we got our first VLBI fringes in this paper that Tomas and I put out. Our other friend is TONE. TONE doesn't stand for anything. It is a array consisting of 8 6-meter dishes. It's an interferometer at Green Bank. Pranav built TONE with his bare hands. You can see in this picture. He didn't build the ones in the back with his bare hands. But tone is a prototype for HIRAX using HIRAX feeds and HIRAX dishes, and also can receive triggers. So in that sense, it's also a prototype for CHIME FRB outriggers, and we've now posted off at Yale. I've shown you some telescopes. There are 3 of them. Now I'll show you some FRBs. Here's an FRB we caught last year in June. It has a DM of about 500 parsecs per centimeter cubed. And it is this FRB which we localized with VLBI at the time of detection. We don't just have one single pulse here. We have a lot of single pulses. There are 9 waterfall plots here, each over the same frequency band from 400 to 800 megahertz. And each of the 3 rows shows our 3 different stations, CHIME at the top, followed by ARO, followed by tone. And each column represents a different single pulse that we've caught with this triggered VLBI strategy. The column in the middle is, of course, the FRB, now shown with higher resolution. And the columns on the left and the right correspond to 2 crab giant pulses, C1 and C2. The reason we chose a declination of 21 is because we get lots of these crab pulses per day, and we can use them as astrometric calibrators. C1 precedes the FRB by about 4 days, and C2 trails the FRB by another 4 hours. And so in this way, we can bookend the FRB in time using these crab pulses, and we know the position of the crab very, very well. There's an active maser at ARO, so there's no clock corrections necessary. There's a passive maser at Green Bank, which we read out with a cadence of 1 second. And there's also a passive maser at CHIME, which we read out at a slightly slower cadence for technical reasons. We read out these masers and clock our telescopes to a GPS clock. And this allows us to, this dual approach of feeding in the maser into the correlator while clocking the telescope on the GPS clock allows us to sort of combine the long-term stability of GPS clock with the short-term relative precision and the stability of these masers. This is a pipeline that was developed by Juan. We wrote a paper validating this method using CHIME and the Pathfinder, which is another telescope located at DRAO on a very short baseline. So I hope I've convinced you that we have all the ingredients for a nice FRB localization. We just need to go into the kitchen and cook up a localization, and this is how we do it. Conventional VLBI experts, I know there are many in the audience, will look at our VLBI array and say, well, you only have 2 baselines. You're also working at sub-gigahertz frequencies. This seems very unconventional. However, our solution to this is not to wait for repeat bursts. It is to exploit CHIME's extremely wide fractional bandwidth. We have an octave of bandwidth from 400 to 800 megahertz, and every observation we have, we observe in 1024 frequency channels. And that's how we populate the UV plane, just with bandwidth, not with Earth rotation. And that octave of bandwidth allows us to eliminate 2 pi phase ambiguities that come up in traditional fringe fitting methods. Essentially, what we do is we can't image since we just have 2 baselines, but we certainly can fit a 4-parameter model. The 4-parameter model sort of goes like this. So the phase of your visibilities I've written here, it consists of a piece corresponding to the localization, 2 pi I frequency times essentially the time of flight delay between the 2 stations. And also a piece that depends on the relative thickness of the ionosphere between your 2 stations. This is sort of the total electron, the slant TEC. I like to think of it as a delta DM because it's a time delay as a function of frequency. This sort of leads to a 4-parameter model where you just have the RA and DEC going into the localization and 2 different thicknesses for your 2 baselines. And if I were only able to measure 1 number, I don't know whether to associate my phase shift with a localization shift or with a delta DM. However, I can measure this phase as a function of frequency over an octave of bandwidth. And I prepared a little GIF to illustrate what this looks like. And I want you to look out for a couple of things. There's some things going on here. First, I'm sweeping the delay from positive to negative. You can see the slope of those fringes change. And now I'm adding some delta dm. And you can see that at the low frequencies, because the ionospheric delay is so frequency dependent, you can start to see that curvature, which comes uniquely from the ionosphere and not from different positions on the sky. We can repeat this for 2 baselines. After this animation finishes, I'll flash to our real data. This is what we've got. We've detected the FRB with the signal to noise of about 30 on both of these baselines, and our phases are shown below. Best fit is shown in green, and here is the fit corresponding to that best to that green line. Our MCMC is 4-dimensional. We have contour you might be interested in is this RA versus DEC contour. You can see it's very multimodal. However, we are able to get our chains to successfully converge by imposing a weak prior on the thicknesses of the ionosphere. And the fact that we saw that plot earlier and didn't see much curvature in the phase as a function of frequency justifies this prior. It's sort of, it doesn't add much information, but it's primarily to help the MCMC converge on a reasonable solution.
1 minute.
Here is what the galaxy looks like. It's this edge-on system. If I were doing DMZ science, this would be one of the host galaxies that I definitely throw out because I'm seeing a sight line that goes right through this galactic disk, and this is corroborated by our radio properties measurements. X marks the spot of our FRB. And you can see our MCMC contours, all those little blobs, lie within these 50 milliarcsecond wide systematic error bands which we've drawn, and the angle is dictated by the angle between our two baselines. My undergraduate, Savannah Carey, who's going to be be on a Fulbright and going to Berkeley the year after, led the optical analysis. She did spectral fitting of the SED and also measured star formation in the kiloparsec vicinity of the FRB. So even though the host galaxy has sort of a modest star formation rate, we do see that with the spatially resolved spectroscopy that we do detect star formation in the immediate vicinity of the FRB. This goes sort of to show that you really need the spatially resolved studies in order to fully determine what's going on with FRB hosts, not just their galaxies. I'm sort of going to skip to the end. I'm happy to talk about the radio data, which I totally skipped over. We've localized at the time of detection an FRB with VLBI techniques, fitted a 4-parameter model to it to localize it, and we've detected star formation in the immediate kiloparsec scale vicinity area. The radio properties suggest a host embedded deep in the galactic disk, coming, very consistent with the young population, totally consistent with the magnetar. The properties, those radio properties, are dominated by the host galaxy because of this nice 3 degrees edge-on geometry that we see. So if you were doing DMZ science, you would definitely, you might consider throwing this one out. Similar to other localized repeaters, we see star formation. However, in our 36 hours of monitoring this burst since, or this patch of sky since August 2018, we have not seen repeat bursts from this broadband FRB. We've measured everything we possibly could on the radio side and many of the things that we possibly could on the optical side. At this point, I'd like to thank all the members of the CHIME FRB collaboration, particularly those of the audience. It's been a real pleasure and privilege to work with all of you, considering many of my close friends. I'll now take any questions, and feel free to message me on Slack. Thank you.
Thank you very much. That's a very good talk. I got really excited to see what you've done with the small dishes at Green Bank site, because I'm building 4-element interferometer at Northwest University, so I was really excited with that. Can you tell me a bit more about your phase solutions? It looks to me that you would have lots of phase problems with the VLBI fringes. What were the phase solutions you got?
I guess I'm not exactly sure what you mean by phase solutions. We are just fitting a model to the phase of the visibilities. And our model has these 4 parameters. It's the RA, the DEC, and the 2 delta DMs.
Okay, what I mean is how big an error do you get in the phases?
How big of an error in the phases? So each...
When you fix your model.
I think, so each of our phases, we have 1,024 phases on each baseline. So each of the phases measured with maybe a precision of about maybe half a radian. And so we integrate that over our whole band and fit that. Let me share my screen and maybe I know I flashed over that really quickly. Let me go back and you can have a look at our fits. I don't know why it's not going. Yeah, so here's our data, and here, so in the bottom plot, I've plotted the phase as a function of frequency. So we have, I've sub-banded them by a factor of 16 here. So you can sort of imagine that any individual phase doesn't give you a ton of information, but by fitting over the whole bandwidth, we can have a good fit.
Yeah, cool. Thank you.
Thank you, Calvin, for that very exciting result. Let's thank him again. We'll move on to another online talk, this one by Marcin Glowacki. Marcin, maybe say hello so we can test your audio.
Testing.
Gotcha. And go.
Hello everyone, I'm Marcin Glowacki. I am a postdoc working at Curtin University in Australia. Firstly, I'd like to begin by acknowledging the Noongar people, the traditional owners of the land from which I'm presenting this talk from. So, yesterday we saw a talk from Keith Bannister and Lachlan Murdoch about craft and craft localizations. They're very beautiful. This is one of them, and what makes this one particularly interesting to me is that we also detected neutral hydrogen gas and emission at the same time as we detected the FRB. A neutral hydrogen gas, or H1 for short, is the star-forming fuel in galaxies, and it's an important component of galaxy evolution. Now, you can detect it with radio telescopes, the same as you detect FRBs with, through the 21 centimeter transition, also known as a spin flip transition. Here you have the hydrogen atom with the proton and electron, perhaps having spins aligned, and if it were to emit a photon of energy equivalent to 21 centimeters, this spins will flip. If you have a sufficiently large amount of these hydrogen atoms in a galaxy, you can observe a spectral line profile like so. And then if you flatten all those frequencies together and look at it spatially, you can get an intensity map. So on the right here, we have two galaxies shown in the optical, pretty close to each other, but not obviously interacting, until you look at the neutral hydrogen intensity map, where you can see that the distribution extends far further out. And this is a key component, especially as we want to understand the host galaxies of FRBs. Firstly, H1 gives you the gas content, not just the stellar, but as signified in that previous plot and on the right here, we have 3 different galaxies and they all contained together within this H1 envelope. So using the greater extent of neutral hydrogen gas, we're sensitive to star formation events, and we can also better trace the recent history of the galaxy, such as galaxy interactions or merger events. And this will be important then in turn to consider the birth of FRB progenitors, and there's been some discussion already in the first talk of this session. Furthermore, if you have, say, spatially resolved H1, then you can do mass modeling, such as through the rotation curve to get a dark matter halo, and that will be interesting for probing the material that the FRB signal is traveling through to reach us. However, number of localizations are still kind of limited, and even more so in cases of FRB host galaxies with H1 emission. There are only, to my knowledge, 3 published cases so far of extragalactic hosts, not including, of course, our own Milky Way. Now, I mentioned on the right, you can see traces of recent interactions or mergers through the intensity map. You can also get an indication of this for spectra, although this can also be due to, for example, AGN feedback. So if you look at the spectrum on the right, this one is quite lopsided or asymmetric. There are many ways to measure this. One way that's been done since the 80s is your measure of flux in one half of the spectrum, say the blue, versus the other half, so the red. And you always take this to be greater than 1 or equal to 1. So using this definition, you would say something starts to be asymmetric above 1.1 or strongly asymmetric above 1.25, for example, looking at the Watts paper. Although there are some small differences in the literature, let's go with this for now. Now, this is of interest because in the Michałowski paper released last year, they looked at the H1 spectrum of host galaxies. And they've noticed that at the time there are only 3, one being the Milky Way, which we know are undergoing mergers. And for the other 2, their spectra were highly asymmetric. And they concluded that this was because of a recent interaction, star formation, and this would support or enable fast FRB channels. For example, a progenitor, that's a massive star, we will show it later. So here are the spectra that they presented in question, and I'm sure you can agree, visually they look quite lopsided, very distorted, and quantitatively that's also the case, values 1.3 or 1.5. This year, we saw a paper from Per et al., and they show the distribution or intensity map here, and you can see it's quite disturbed. The pink star, which I'm highlighting here, is the location of the FRB to the spiral galaxy. And you can see just around there, there's a deficit of neutral hydrogen gas. And also the emission is quite unsymmetric. like with the Jankowski paper, they also concluded that there was a recent merger happening for this host galaxy, and this would have possibly supported large stars being the progenitor for the FRB massive star. So that's 3 in total. There's one more which I won't show any images of today, but keep an eye out for Ryder et al. Coming soon to a journal near you. This is another FRB host galaxy that we have follow-up H1 emission. We see the spectrum is lopsided. We see signs of interaction otherwise. So in each of these cases, which is 4, they have H1 spectrum or distributions that show clear signatures of a galaxy interaction or merge activity. And this has led to starburst activity happening recently for the host galaxy, and this could be a pathway to the FRB progenitor. So let's add one more to the sample size. This is FRB211127. This was a commensal detection during ASKAP observation. So this was by the craft survey. We were able to trigger a voltage dump and localize this FRB to a nearby spiral galaxy. But the key point of craft is that it's commensal. So ASKAP is conducting its own surveys, and craft just looking over their shoulder and triggering voltage dumps whenever we notice an FRB. And in this case, this was during a Wallaby survey observation. This is a H1 emission survey to cover the whole southern sky. And this was one observation of 2 pointings towards a larger field. And we've been able to collaborate with them to see if there's any H1 in the host galaxy. Now, this beautiful picture comes from VLBI imaging from follow-up by the craft team. So the white ellipse that's very small in the center of the screen is the localization. So it clearly matches, and the redshift also matches with the DM of a bit over 200. And here's the FRB signal itself. We only see one feature at this time resolution. And this is all work that will be presented in Dell et al. So keep an eye out for that paper as well. Now, if we zoom out of that first picture and we overlay the contours here, this is the H1 emission that we've seen with Wallaby. We don't really see something that's quite as disturbed as before. There is one small feature to the right of the screen, but this might just be a factor that is it just might be an artifact rather than something like an actual tidal tail. And even if it is a real disturbance, it's far away from the actual FRB localization. And otherwise, the distribution is fairly symmetric, so there's nothing too remarkable here. Now, what about the spectrum? Oh, this is on the left. And by eye, you can see there's a little bit more flux on the left-hand side compared to the right. But again, this is not something that's quite at the same level as seen before. We have a slightly asymmetric quantitative value of 1.16, but this is well below the limit, so-called of 1.25, and far below that of the Mihalkovsky papers. And on the right, we're also showing the radio continuum of the galaxy. So this shows that there's definitely some radio continuum associated with the host galaxy of this FRB. And there's no continuum showcased for that little blob of intensity on the right as well, suggesting it could be just an artifact. So this is the first extragalactic FRB host galaxy that we've detected in H1 emission with no clear telltale sign of galaxy interaction or merger event. It's definitely far less asymmetric than before. Again, compare the spectrum on the top compared to the one on the bottom, which is for our host galaxy. So we break the early trend, and this will be all part of work that will be submitted shortly. But to finish off, I will stress we've just gone from a sample of 4 to a sample of 5. We have only 5 extragalactic examples here, and we really need to up the numbers. Luckily, Craft, alongside of the Krakow upgrade, will greatly increase the rate of localized FRBs, and we'll have excellent synergy, including with the H1 emission surveys with ASKAP, such as Wallaby and Dingo, so we can greatly increase the sample size and better study the host galaxies or FRBs in the gas components. Thank you for the opportunity to talk. I'll take any questions.
Thank you, Marcin. Questions from the audience or online? I'm not catching any. Marcin, I guess you were so clear, they were completely convinced in your presentation. Thank you again.
Hello everyone, my name is Fabian Jankowski. I'm a research associate at the University of Manchester. I want to switch gears slightly here. Today I will talk to you about the implications from the first MeerTRAP Fast Radio Burst sample. And in the first part, I quickly introduce the sample, And in the second part of my talk, I give you the implications that we have already from the MeerTRAP surveys. Let me quickly, before I start, let me quickly acknowledge the MeerTRAP collaboration. The work that I present here is by a lot of people from a lot of different institutions, and MeerTRAP is led by Ben Steppers. MeerTRAP was already introduced yesterday. MeerTRAP is a fully commensal project at the Meerkat telescope, and we have a huge amount of time on sky and sky coverage at excellent sensitivity. And what is mostly important for this talk is that we perform two surveys at the same time. One that uses the incoherent beam that is slightly less sensitive, with a field of view of about 1 square degree. And the second one is about 5 times more sensitive, where we tessellate the primary beam with coherent beams. And we have been operational since about late 2019. Let me get into the first part. These are the 11 FRBs that we have discovered until the end of 2021. These are the ones at L-band frequencies, and they have dispersion measures between about 400 to about 2,000 units, and XSTMs between about 100 to 1,900, which places them at the M-inferred redshifts of 0.1 to 2 approximately. And many of these are quite faint. They have peak flux densities of about 60 millijanskis and up to about 1.4 janskis at the high end. And in terms of morphology, some of them are dominated by dispersion measure smearing within a channel. Some of the others show nice exponential scattering tails that you can see here, and others show maybe some hints of complex structure, maybe some two double peak components. In terms of localization, we do that by tessellating the primary beam with coherent beams, and we apply the tidal beam localization technique. And depending on if an FRB is only detected in a single coherent beam, we can localize it to about 1 square arc minute, which is already better than about the vast majority of FRBs that are currently published. If it's detected in multiple beams, we can go to about 500 square arc seconds. And if we can actually image the field or image the voltage buffer dump, we can get down to about 1 square arc second or below that. The next thing that I want to speak about quickly is scattering, because that's a quite important measurable quantity for FRBs, because it directly probes the turbulence in the ionized media that an FRB traverses, such as the host galaxy, the IGM, any intervening galaxy, and then the local environment, the Milky Way halo and the ISM. And I just show you an example here of an FRB that shows a nice scattering tail with a scattering time of about 12 milliseconds. And if you look at how the scattering time scales with frequency, you can derive the scattering index, which is minus 4.6 for that FRB, which is very similar, or which is consistent with being Kolmogorov turbulence. Out of these 11 FRBs, 3 show significant scattering, 1 shows a slight hint, and several others are limited by dispersion measure smearing. And for those that show significant scattering, those are consistent with being Kolmogorov, which is different from what we know from pulsars, from galactic pulsars. Okay, the next thing I want to quickly talk about is host galaxy association. And obviously the idea is to get the host galaxy spectroscopic redshift, and we use the PATH software to do that. The PATH software assigns a prior probability for each galaxy within the localization region based on secure host associations, and then computes the posterior probability. And here I show an example for, this is the localization region. This is one of the FRBs that was discovered in a single coherent beam. And these are the 4 galaxies. However, the posterior probability is only about 30% of galaxy 1. and there's a 35% chance that the host was not detected in that image because it's quite a shallow image. If you assume that all the galaxies detected, it increases to about 50%, and the galaxy is at a redshift of 0.5. The next thing that I want to talk about quickly is something quite interesting, I think. In some of the FRBs, we have detected post-cursor bursts, and this is what I show you here. You can see there is a post-cursor burst at similar DM approximately about 200 milliseconds after the primary burst. And this is actually the second FRB in which it was a post-cursor burst was discovered. And interestingly, the burst separation is quite similar. It's also about 200 milliseconds. And there's even another FRB that shows maybe a faint secondary component here. So what does this mean? Are these repeat bursts? So are these repeater candidates, or is this a secondary emission component, for example? Or are these maybe some echoes or lensing effects or something like that? I think this is quite interesting. In the second part, I want to quickly talk about what we can learn from the MeerTRAP survey so far. Because since 2019, we have spent a considerable amount of time on sky surveying the sky. This is the survey coverage that I show here. We have spent about 318 days on the sky. And what can we learn about the FRB population based on that? Based on the FRB yield that we have so far and the survey coverage, we can compute the inferred all-sky rates, the inferred FRB all-sky rates, and these are approximately 2,100 and 4,400 FRBs per sky per day for the coherent and the incoherent survey above a limiting fluence of 0.7 and 3.4 Jansky milliseconds. So these are quite high. So what can we do with these all-sky rates? We can already do some limited cosmology, and this is what I want to show you here. I show the inferred FRB all-sky rate against the limiting fluence for various surveys, and the MeerTRAP data points are the blue ones here. And the nice thing is that we have these two independent surveys that are going on at the same time. So we have a nice lever arm here. And what you can see here is if you fit a power law to the data, you can see that the power law is shallower for the MeerTRAP surveys as it is for the shallower surveys. So what does this mean? It means that maybe there's a break or some turnover in the rate versus fluence distribution. So there's apparently some deficit of low fluence FRBs. And so what does this actually mean? The rate versus fluence distribution traces the source count distribution of FRBs, and we think that this flattening might be due to cosmology. So maybe we have discovered a higher redshift sample where cosmological effects are become more apparent, or maybe there's progenitor evolution happening. So I think this is quite neat already because we have these two data points. Yeah, that's already my summary. Thank you very much.
Question for Fabian.
Hi, Fabian. Thank you for the nice talk. I'd be curious to hear about the post-cursor bursts. How significant is it? Can it be just due to, for example, noise that somewhat aligns, or are these somewhat significant? Like, would you detect those if it was by itself, for instance?
Yeah, so the first one that I showed, let's see if I can go back. The first one that I showed is we wouldn't classify it as an FRB if we had detected it only by itself, but because we have the previous information already about the dispersion measure, we think it is real. It has a signal to noise of about 5.8 or something. For the other one in Kashtup's paper, I think it's even a little bit higher than that. Yeah, but yeah, that's what I can say.
Okay, thank you.
Question from online. Clancy's James says he didn't see the value of source counts you derived nor the plot where this is fit. Can you highlight that?
So
or maybe just you went through it a bit too quickly for him.
So I think he is talking about this. What was exactly the question? So
the value of the source counts you derived and the plot where that was fit.
Okay, that's essentially the plot here. So these are the all-sky rates, and these are the posteriors from the fit. And you can see there is a 95%. There's a difference at 2 sigma significance. Does that answer the question?
I think it does. Thank you. Please.
Thanks for the talk. Does the rate that you report account for selection biases? Like, could it be that you are missing low fluence FRBs because of some observational biases and that's leading to a different slope?
Yeah, I mean, there are various caveats, of course, because we haven't detected so many, or we haven't reported on that many FRBs so far, and maybe that will change in the future as also maybe the system gets refined more. Yeah, that might be one thing. It might also be another thing is, if you can show the slide again. Another thing is that all these data points are also, they have all their different selection effects in there as well, right? So if it might also be that this slope is driven significantly, I mean, it's clearly driven significantly by ASKAP and CHIME. So there are various caveats in there, of course.
Okay, great. Thanks.
Last one.
Hi, Fabian. That plot again with the rate against fluence, if it didn't turn over, how many would you have detected?
Yeah, if it didn't turn over, we would have detected, I think, what did I calculated it in the paper. I think it would have been like 60 or something like that. So it's quite unlikely that we have missed so many.
Yeah. Okay, thanks.
Great. Let's thank Fabian again. And that ends this morning's slew of sessions. We'll be back at 1:30 Korean time. Thank you. Thanks. Tech support.